Alright, in this short video, I will demonstrate evaluating limits using L'Hopital's rules. I will first give an introduction of what L'Hopital's rule says and then give a particular example. Alright, so L'Hopital's rule, which is abbreviated as L apostrophe H and R. The L is usually lowercase. It says limit of f of x over g of x as x approaches a certain number a, whether it's finite or infinite, is going to be the same as limit of f prime of x over g prime of x as x approaches to a, and that is equal to a certain number L, where L again could be finite or infinite. Okay, this rule is particularly used when we have indeterminate cases of the form either 0 over 0 or infinity over infinity. Of course, you can have plus or minus. These are called indeterminate cases. Indeterminate cases. In particular, this indeterminate case is fractional because you have a fraction. But a lot of limits could also be giving you indeterminate case, could be either infinity to the power of infinity, infinity times infinity, or 1 to the power of infinity, or 0 times infinity, or even infinity minus infinity. You could have any of this form in evaluating a limit, and these are all called indeterminate cases because you cannot determine what the actual value will be. So what we're going to do is I'm going to just use this rule into a particular example where a lot of my students were struggling in an assignment. So this is what it looks like. It's limit 9x over 9x plus 15 to the power of 2x, and the x will be approaching to positive infinity in this case. It's a typical example. You can just take to negative infinity, it doesn't matter, and these numbers could change, but just this one is a typical example. So what I'm going to do is I'm going to do a little bit of algebra because this one is really upon substitution. This is going to be 1 and this is infinity, so I have really 1 to the power of infinity indeterminate case. Okay, it is an indeterminate case, but it is not one of the cases where I can apply the L'Hopital's rule. So what should I do? I will use algebra to change it to one of the forms. And this is what I'm going to use. If you consider an example, y equals x to the power of x, and I take the natural log of both sides, the natural log of y will be the natural log of x to the power of x. As you remember, the exponent is dropped down to be a coefficient using the rule of logarithms. So therefore, this will be natural log of y equals x times natural log of x. Well, notice that the base is e, and when we change from logarithm to exponents, the base remains the same. So if I really tend to solve for y, this will be y equals, the base is e, to the power of the answer. So e to the power of x natural log of x is what y will be. Well, but y was already x to the power of x. So y is also e to the power of x natural log of x. So therefore, this is the same as x to the power of x. So in my example, what I'm going to do is I have like x to the power of x. Of course, not x exactly, but it's something to the power of something with in terms of x. And I'm going to apply this one to just make the base to be e. And I have natural log. And I will work my limit on the exponents in this case. So if I apply this property, very powerful property, to this one, I'm gonna have my limit to look like this. This will be limit as x approach to infinity, e to the power of 2x times natural log of the base 9x divided by 9x plus 15. Okay? Well, notice that this 2 times x as x approaches infinity is infinity. Natural log of 1 is 0. In fact, any logarithm of any base logarithm of 1 is 0. So this is changed into from 1 to the power of infinity into infinity times 0 in determinate case. Determinate case. I'm almost there now. I can change this one easily into 0 over 0 form. So the way I would do it, I will first, of course, using properties of limits, change this one into e to the power of limits of 2x times natural log of 9x over 9x plus 15 as x approaches to infinity. So this is a property of limit where the limit goes to where there is x, where it's applicable. So e to the power of this number. So what I'm going to do is really, I'm going to leave the base and work my limit right here. So I will just for now leave the e, work on this one, get whatever this is, let's say it's a certain number a, and my final answer will be e to the power of whatever a will be. Okay? So let me just go ahead and do that. Okay, so I have limit of 2x times natural log of 9x over 9x plus 15 as x approaches to positive infinity. So I'm gonna, like I said, it's gonna be infinity times 0. I will bring this one to 1 over 2x. So limit of natural log of 9x over 9x plus 15 over 1 over 2x as x approaches to positive infinity. Okay, so now I have a certain function f and another function g. So I'm going to apply the Hopital's rule because this is 0 over 0 indeterminate case. Determinate case. Before I do differentiate, what I'm going to do is I'm going to use the rule of logarithm to just expand this one a little bit. And that rule is, if you remember, the natural log of m over n, lowercase, it doesn't matter, uppercase, is natural log of m minus natural log of n. I'm going to use that one for the numerator. So this will be the limit of course, as x approaches to infinity of natural log of 9x minus natural log of 9x plus 15 over 1 over 2x. 1 over 2x. Now I have my f and g, I differentiate them. Okay? So when I differentiate, I'm going to use chain rule. I'm sorry, I have a small board erasing fast. Hopefully you are following me. So this will be limit of the derivative of natural log of 9x is 9 over 9x minus the derivative of 9x plus 15 is 9 and then 9x plus 15 in the denominator because of the natural log over the derivative of 1 over x is negative 1 over x, but I have half, so that's negative 1 over 2x squared. And then this will be as x approaches to infinity. Well, a simple algebra, this will be reduced to 1 over x. So LCD, or least common denominator, is going to be x times 9x plus 15. So this goes here, this goes right there. So this will be limit of 9x plus 15 minus 9 times x is 9x over x times 9x plus 15, which is the least common denominator, divided by negative 1 over 2x squared. And this will be x approaching to infinity. We're almost there. So this is reduced, of course, they cancel each other. So this goes up here, So rational fraction, what is called complex fractions. So this will be the limit of negative 2 times 15 is negative 30 x squared over 9x squared plus 15x as x approaches to infinity. Well, remember, when we have a rational function and the x is approaching to infinity, all we're going to do is we divide both sides, every term by the highest exponent, which is x squared. This will be x squared, so that's negative 30 over 9. This will approach to 0, so therefore the limit will be negative 30 over 9 as x approaches to infinity. Of course, you don't even need this step. You just have your answer negative 30 over 9, which is reduced to negative 10 over 3. So really that's my A. So therefore, the limit, my final answer, the limit of 9x over 9x plus 15 to the power of 2x as x approaches to infinity will be e to the power of negative 10 over 3, which is exact value. By the way, you could have done this one by simply taking the logarithm and then solving for y instead of whatever I did, but this is the best way, I think, in my opinion. So that's exact value. In fact, a good practice that I would leave for you would be to find out what will be the general case if I have limits of, say, a certain number, arbitrary number a times x plus b divided by, you could do the same number ax plus c to the power of dx as x approaches to infinity. Or you could even just leave this one aside and just do ax over ax plus c to the power of dx. What will the limit be in general? Does it depend only on a and b, on A and D, on a and c, on what are the parameters that will determine what is this value going to be? So I really want you to try it, and if you have any idea, put it on the comment section. Also, if you have any question about the clarity or the content of any of this clip or video, please just write in the comment section. All right, thank you. Bye-bye.